It's a pleasure to have Riccardo Sturani to talk today. He's the new member of IFT. He graduated at the Scuola Normale Superiore, sorry for my Italian accent. After that, he made some postdocs at Helsinki, Geneva, Urbino, and in São Paulo, here at SAIFR. And after that, he was hired at the International Institute of Physics in Natal. And now he's here as a permanent member of IFT-UNESP. And he is going to talk to us about gravitational wave astronomy and precision gravity. Thank you for accepting our invitation.
Okay, thank you for giving me the opportunity to educate more people to the wonderful world of gravitational waves. So now that I lured you in with the title talking about precision gravity, so you might think I will talk about fundamental physics and how to do computation, precision computation in gravity. Actually, no, you have to wait for 15 minutes before I will tell you about the observations, about the experiment observation, and only then I will go to the topic of how 50 methods that have been historically developed for particle physics have been very, very, very useful in getting phenomenological consequences for the analysis of gravitational waves. And on the converse, and to give something to do to the people to the huge particle physics community who might have been tired of doing computation in particle physics and wanted to apply their huge amount of knowledge to something else. But before going there, let's talk about the observation. So this is how the interferometer works. So in the interferometer there is a laser. The laser is a source of coherent light. So it's very important, it's coherent, so it has a very definite phase. It goes through a beam splitter, it's separated into two beams at 90 degrees, it hits the mirror, which are a few kilometers away, and then when it recombines, the intensity of the recombined light is dependent on the relative phase. For instance, if they are in oppositional phase, there is zero intensity, but then if something happens and the mirror shakes, and so the travel path of the light changes, then the intensity of the recombined light changes. So basically the intensity of the recombined light is a direct measure of the differential motion of the mirror. Of course, if I move the mirror in the same way, it doesn't show up. The differential motion in the mirror will show up in a change in the intensity of light. And then another important thing to notice is then the gravitational wave, which is transverse. If it arrives at 45 degrees between the two mirrors, then it gives zero signal. Of course, because if it arrives from the direction which is completely symmetric with respect to the apparatus, it gives zero signal. So this device is sensitive only to gravitational waves that affect asymmetrically the two mirrors. For instance, prototypical, if the gravitational wave arrives perpendicularly, that's perfect. But basically, any other direction which is not 45 degrees in the plane of the interferometer is giving some signal. So let's go back to the presentation. So, and this is not real, this is of course over simplification, because these are a few kilometers apart, and here there are cavities, which are called Fabry-Perot cavities, that allow the laser to go back and forth a few hundred times, so the actual optical path is multiplied by a few hundred. And this allows to measure, the phase difference that this kind of devices, this interferometer, are allowed to measure by present technologies of the order of 10 to the -8. So this is fixed by technology. The minimal phase difference that one can measure. Then, of course, you can play with the laser wavelength and with the number of bouncings of the light to get the actual delta L that you can measure. And the delta L, you know, in general relativity is proportional to the h. The gravitational wave disturbance will cause a movement of delta L of this mirror. And the minimum delta L that can be measured by plugging in this 10 to the -8 and the wavelength of the laser, which is of the order is the near infrared, so it's of the order of hundreds of nanometers. The minimum delta L that can be measured is 10 to the -15 divided by the number of bounces in meters. So this tells you that this device is able to measure the differential motion of the mirror, which is of the order of a nucleus, actually smaller than the nucleus of an atom. This is because this laser is really macroscopic, it's not it's macroscopic, it's not microscopic. I mean, it's laser, when it hits the mirror over there, it's something like this. So it measures the average position of a macroscopic number of atoms. It doesn't measure the position of a nucleus of an atom. That's why it can reach this kind of science fiction sensitivity. Questions?
No, now I understand why how we can reach such a sensibility.
Yeah, because it's average over, you know,
I see.
the piece of the mirror that is hit by this laser is something like that, few centimeters square.
Okay.
Of course, the laser is very collimated, but still over a few kilometers, it spread a little bit. There were other questions? So, so this is meters. The unit comes from lambda, and basically the higher the number of bounces you get, the smaller is the minimal difference that you can measure. So if you could make a Fabry-Perot cavity that would go 100 times more, then you would reach the sensitivity. But then, of course, it's a subtle play of compensating the loss and everything. And also, you know, you might think, well, why don't we choose a smaller wavelength? Well, this is really a science material problem, because if you look at the mirror, they're actually transparent. If you look at them, if you look with visible light. This mirror, they've been engineered to have very close to perfect reflectivity, exactly in a narrow bandwidth that is exactly the wavelength of the laser. If you change the light a little bit, then the mirror are really not mirror, but are transparent glasses. So it's a real, you know, fine-tuning of all the technicalities that you have of all the tools that you have to reach this science fiction sensitivity. So, and this is just to summarize. The detector, I mean, the gravitational wave physics is not linear, but since gravitational waves are so tiny and so small, you can treat linearly, and you actually make a very, very small error if you treat everything linear. So, the signal that you measure the detector will be a combination of the two polarizations. I mean, of course, I didn't tell you, but I mean, everybody is familiar that in general relativity you have two polarizations, like for the photons. I mean, any massless field has two polarizations. So, just heuristically, you can accept that the signal that you measure is a linear combination of the two polarizations. Why linear? Again, because the gravitational wave is so small that you can neglect no linear effects. And by definition, the coefficient of these two polarizations that hits the mirror are called F plus and F cross. So we measure for each detector, we measure this combination of the two polarization. So the F plus and F cross of each detector, so detector in LIGO Louisiana and the LIGO Washington can be computed according to the position in the sky. What actually matters is the sum square of these two, which are called pattern functions, these two coefficients that says how the polarization affects the detector, and basically for each detector you have maximum sensitivity on the top of it, for signal coming on the top of it, and you have zero sensitivity for those four directions that are in the plane that affect symmetrically the two mirrors. And so the two LIGO detectors in Washington and in Louisiana are so arranged that you see the top sensitivity and the zero sensitivity direction are aligned. So if this detector sees something, this detector should also see something. Whereas Virgo in Italy is arranged in a completely different way. So you see the zero sensitivity and the top sensitivity are completely misaligned. This is to tell you that if you see something in the two LIGOs, that doesn't necessarily also show up in Virgo. And vice versa. I mean, of course, you need at least two detectors to gain confidence of the detection, but then having a third detector will allow you to cover the space that you have lost with the definite alignment of the first two. Okay, and these are the real pictures of the detector. This is the one in Washington, this is the one in Louisiana, this is 4 kilometers, 4 kilometers, 4 kilometers, 4 kilometers. The one near Pisa is 3 kilometers and 3 kilometers. And so,
just for curiosity, the alignment between Virgo and LIGO was going this way in purpose, or it was just for chance?
No, well, basically, the only important thing is that they were not perfectly aligned, so you can cover the blind spot of LIGO. And then, of course, you have infinite choices of not being aligned.
I see.
And then basically the choice of the alignment was just on basically which field was easier to buy and so on. You know. Of course, all these land, I mean, differently from the States, this land is heavily populated in Italy. So you need, I mean, it's much difficult to build something in Italy than in Washington. So there has been 3 science runs that ended. The first one lasted for 4 months. I mean, actually 50 actual days. Of course, the detector not all the time. Then so the very first historic detection plus 2 others. The second. With the second science run, we got to roughly 10 detection, and Virgo joined only in the last month of the second science run. And then there was the third science run that lasted almost 1 year. It was shut down 1 month before the schedule because of the pandemic, you see. And we got overall to 90 detection. So in April, in the last month of the third science run, the Japanese detector was supposed to join. But he joined, actually, he turned on its own because the pandemic made LIGO and Virgo to shut down, whereas the Japanese went on like scheduled, but it was alone and it was very small sensitivity, so didn't see much. And by the end of this decade, we don't know exactly when, the Indian detector should also be on. Okay, so this is just a one slide crash course in gravitational waves for the students. So basically the amplitude of the gravitational wave is proportional. So there is a g Newton, of course, there is 1 over the distance, of course the amplitude decays as the distance, and then there is the second derivative of the quadrupole. Basically the second derivative of the quadrupole gives you the quadrupole, which is the second moment of the energy, gives you the kinetic energy. So basically the amplitude of the gravitational wave is the kinetic energy of the source system divided by the distance. And of course, then it's always much smaller than the Newtonian potential sourced by that very same source. What makes it possible to detect is this typical time behavior signature. The potential of the source is constant. Think of an extragalactic source of 1 solar mass. It will give absolutely negligible potential here that nobody will ever measure. But the same source having a time oscillation, having a non-trivial time behavior, will give not in the Newtonian potential, but in the gravitational wave, a pattern of oscillation that we can measure. So the typical frequencies are around the kilohertz for the system, which are 10 kilometers. I mean, the typical distances we are talking about is 2 sources of few solar masses at tens of kilometers away, emitting at the kilohertz or a bit less. And the typical velocity when the sources get very close together are non-negligible fraction of the speed of light. So what is important here for cosmological application is that the amplitude is not only modulated by the strength of the source and by the inverse of the distance, it's also modulated by some angles that basically tells you what is the orientation of the plane, of the binary, with respect to the viewing direction. So L is the angular momentum of the system, N is the view direction, so these angles give a modulation. So you cannot really tell what is the distance of the source until you know also this geometric factor. And this is important if you want to apply to cosmological situation, because for cosmological situation you want to measure the distance, and the distance is degenerate with this angle. Of course, the nice thing is that this viewing direction this viewing direction is the same for all detectors on Earth. The detectors on Earth, they're not so far apart that it changed the viewing direction over a scale of megaparsec, of course. But what can change between different detectors is the pattern function, the coefficient that I showed you earlier, that multiply this function. So if you see really this 2 polarization with different coefficient, which is not the case for the 2 LIGOs, but is the case if you really see the signal with Virgo, then you can disentangle the 2 separate polarization, and then you can disentangle the distance and this angle. But as long as you see the same combination of the 2 polarization, you cannot disentangle the distance and this angle. And then another point which is important mentioning is that we don't measure redshift, of course. Well, of course, I will demonstrate you in a second. What we measure is the mass, the strength of the source, and the distance. And then we measure things with respect to the measure in observer time. If with respect to the source time, since the phase is dimensionless, it can only depend by the time divided by the total mass. The mass in gravity is the same dimension as length or time, because gm is a length. So the phase is dimensionless, it cannot depend on time alone, can only depend on time divided by mass. If you rescale everything to the observed time, then there is a 1 plus z appearing here. That means that the mass that you fit from the shape of the signal is the redshifted mass. And then if you make the amplitude depends on the redshifted mass, then here you have a co-moving distance times 1 plus z. This is the luminosity distance. This is the redshifted mass we measure from the pattern of the oscillations. And so we have no way to measure the redshift. We measure luminosity distance, which is this combination. We measure redshifted mass, which is this combination. So at most, we measure the luminosity distance, but modulo is degeneracy with the angle. We measure the redshifted mass, but we don't measure the redshift separately. So we have information about the distance, modulo is degeneracy with the angle, but we don't measure the redshift. So we cannot do cosmology immediately once we measure something, because we get the distance, but to do cosmology you need distance and redshift and to relate the two. So you need some extra input. Okay, phi is the phase of the binary. The typical source is the binary system, and phi is the phase. Basically, the modulates the motion in the plane. And basically, the two polarization, one goes, roughly speaking, with the cosinus of this phase, and the other goes with the sinus of this phase. So, what is your question about phi? I don't know.
So it's periodic.
So the motion is periodic. The prototypical source is a binary system in circular motion. Prototypical source. Yes, the second derivative of the quadruple gives the kinetic energy, because the quadruple is the second moment of the mass, mxx.
No, I'm just asking, so you have something with frequency f, and there should be like f squared in the right?
No, I mean, the second moment, no? Okay, this is xx times the mass gives the mass times cosinus squared. Once you derive it 2 times, it's always a cosinus. And then you get the power of v squared. Sorry, I don't understand. V is the typical velocity of the binary system. So the second m, this is mxx, you derive 2 times is mvv, basically. Then you can, of course, by the Kepler's law, you can relate the velocity to the frequency, and you get the standard form that you find in textbook. The frequency goes as the velocity to 1/3. Okay. So we measure this redshifted mass, we don't measure the intrinsic mass, and we measure the luminosity distance. At most. Okay, and this is the summary of what we have seen so far. These are the 90 detections. So this is the scale, 10, 20, 50, 100 solar masses. So just to frame this in context, all of these are, of course, extragalactic. No? Our galaxy is the size of a few tenths of kiloparsec, and the closest signal was at 40 megaparsec. So these are really extragalactic signals. We don't see things in our galaxy, not because we have anything against our galaxy, but because these systems are very, very rare. I will tell you in a second what are the rates, but this happens once every million years per galaxy. So if we could only be sensitive to things happening in our galaxy, we would never see anything within our retirement age, not even the youngest among you. But luckily, the intensity just drops as 1 of the distance, differently from electromagnetic radiation, whose intensity drops, because in radiation you measure not field, but the intensity. So the intensity goes as 1 over d squared, so you don't see too far. The gravitational wave, despite interacting very, very weakly, they decay only as 1 over the distance, so we can see up to the gigaparsec. So when we look at up to the gigaparsec, we can see billions of galaxies. So despite the event being very, very rare in each galaxy, if you can see over a billion galaxies, then you have a good chance to see things. And actually at the end of the third science round, we were actually detecting one event per week, roughly. So, and this is the region of masses, 20, 50, 100, you see after the merger it could get to something 150. Why? Why we don't see higher than that? Well, because a black hole has a size which is determined by its mass. So the larger the mass, the larger it is. But if it is larger, then it takes longer to go around its companion and the frequency goes down. And this detector cannot see below 10 Hz, just because they lay on Earth. And on Earth there are a lot of noise around the 10 Hertz. I mean, basically vibration, cars driving by, planes, agricultural things happening, and so on. So below 10 Hertz, forget seeing anything with a detector that is sitting on the surface of Earth. So forget seeing any black hole with masses over 100 solar masses. We just can't with detectors sitting on the surface of the Earth.
My question is, are there two events, neutron stars?
Yes, the two events neutron star. One was the famous in August 17 that gave rise to the electromagnetic counterpart. The other didn't have any electromagnetic counterpart. No. But you know, it's.
What's the explanation for this?
I mean, it's very hard. I mean, it was much farther distance. It's difficult to find the transient, and the mass. The masses, you see, the masses were larger. It's not unusual. I mean, if you have smaller mass, you have higher tidal forces. You know, the tidal forces goes as m divided r cubed, and r is of the order of the mass. So the tidal force is 1 over mass squared. So the smaller the mass, the larger tidal forces. The larger tidal forces, the easier it is to break your companion. So the higher the mass, the smaller are the tidal forces. So the higher the mass, you just smash without breaking. I mean, this is not a theorem, but you know, the higher the mass, the less likely you have a breaking. And you know, the electromagnetic counterpart is due to the fact that you know the neutron star breaks and you have free charges all around that emit light. If the masses go up, you have less chances to have a breakage.
But even so, neutron stars in general, they are more or less, they have more or less the same mass. I mean, would it be so? Anyway.
Yeah. Anyway, I mean, the point is that the jet could have not pointed to us.
Yeah,
So once you have the breakage, you have a jet, and then you have an isotropic emission. The problem is that the isotropic emission is not very strong. You don't see it if it's with the present detector. You don't see it if it's beyond 200 megaparsec. So it's absolutely no problem that we didn't see any. I mean, and also there is another problem that there are a lot of transients in the galaxies which are supernovae. You know, collapse of single stars, not neutron stars smashing into another star. And these are much more common. This happens once every 100 years, not once every 1 million years. That means that if you look randomly in the sky and you look for a transient, basically over 1 million times over 100, you see supernovae. No? If you just look blind, you say, oh, let's look at there, let's look for a transient. So 1,000, if you just look randomly for a transient, the chances of being a supernova with respect to being a binary neutron star is 1,000 to 1. And the localization that we have in gravitational wave is very poor. So if you just take a big patch in the sky, very far, and you look for a transient, this one was very lucky because it was 40 megaparsec away. 40 megaparsec is really in our backyard, basically. So that's why I mean there is a huge effort for future electromagnetic detectors to see counterparts of kilonovae up to a few hundred megaparsec, which we are not able to do now. So just to wrap up, I mean these are the black holes which are called solar masses from 1 to 100-ish. Are black holes with the higher masses known? Yes, there are supermassive black holes at the center of a galaxy with a mass of 10 to the 6. You know, it was the Nobel Prize 2 or 3 years ago. And then there are supermassive black holes that are feeding the AGNs, active galactic nuclei. They are eating a lot of matter, and they are 10 to the 9 solar masses. And then what's in between? Between few hundred and 10 to the 5. These are called intermediate mass range black holes. Do they exist? We believe so. We've never seen. We won't be able to see with LIGO Virgo, but probably with other detectors that can stretch the frequency to smaller frequency than 10 Hz. So, solar massive black holes we see plenty. Even before gravitational waves, we have seen solar massive black holes which were eating matter from a companion. Supermassive black holes we have seen plenty. Intermediate massive black hole, we don't know. They should exist because I mean it would be very strange that they stop at 100 solar mass and they reappear at 36, but we have no observational evidence. Okay, so this is the typical noise curve of LIGO Virgo. This is a real one. This is design sensitivity. You see, this is 100. This is what is this? This is I think this is 60 or 50. This is the power line of either Virgo or LIGO, 50 Hz or 60 Hz. And then you see when you go 40, 30 Hz, then it's very much degraded. And these are the typical signal that hit the detector. And they die, of course, at a frequency which is inversely proportional to the size, so it's inversely proportional to the mass. Okay, and this is to show that basically what you expect, how you expect to build a solar mass black hole. So for stars up to 25 solar masses, you expect to have a neutron star. For stars bigger than that, you expect to have a black hole, first by a fallback of the material, and then by a direct black hole collapse. And then you expect to have a gap by stars in this range. Stars in this range would have an internal pressure so high that they are basically unstable by production of electron positron. There are so much pressure in the photon in their core are so energetic, they can produce pair of electrons and positrons, and they can basically explode. So you expect to see a gap in stars in this range that would reflect in a gap in black holes at around 60. So you shouldn't see black holes from astrophysical collapse of stars in their mass range between 60 and 100, but we saw few, so we don't really know what's happening there. Maybe those black holes were recycled, where merger of two black holes were recycled in the binary system. Maybe this limit is not so strict, but I mean this is a very active line of research to investigate what is happening, why we don't see this gap of black holes around 60 solar masses. Okay, so these are, I just pick few events randomly. And you see this is the typical localization. So for signals seen by two detectors, the localization is a circle in the sky that in this coordinate is banana shaped. For detection made by the three detectors, you really see a small circle. But this is to tell you that these localizations are usually huge. You have zillions of galaxies in these regions. This was the 170817. It was the double neutron star. It was amazing. And so with this, it was possible to see. It was seen together with the gamma ray. The gamma ray localization was even worse than this. But then, just by patching the sky, people look for the optical counterpart, and the optical counterpart was found with basically 0%. I mean, the actual galaxy was identified. But this patch in the sky would contain, I don't know, up to 40 megaparsec will contain hundreds of galaxies or thousands of galaxies. Just up to 40 megaparsec. If the signal is farther than that, then of course it scales with the cube of the distance. Okay, and this is the rate that we have measured. So look at this, the blue line, the blue bands, these are rates in megaparsec cube per year. You have to consider that in a volume of 1 megaparsec cube, there is a little less than a galaxy, roughly. A little bit less than a galaxy in 1 megaparsec cube. So basically you can translate this 10 to the minus 6 in 1 mega year rate per galaxy. So this is for binary neutron star. This is the range we can bracket with the detection we have so far. This is for a neutron star black hole. This is the range we can bracket. And this is for binary black hole. This is the range. Of course, we have many more binary black holes, so this bracket is smaller than the other ones. So the nice thing is that you see this blue band is the prediction of 10 years ago. 10 years ago, you can look at, actually more than 10 years ago, oh, sorry. You can look at this paper. Okay, it's half cut. But there was this band, which were the astrophysical prediction of binary neutron star merger. And you see, we are falling more or less inside the prediction of 10, 15 years ago. And these are kind of the most probable numbers that were given a few years ago. Only the binary black hole we have been more lucky than the prediction. This gray line were the upper bound 10 years ago. 10 years ago there was no detection, so these were the upper bounds. So you can see, 10 years ago, people were not worried that we were not seeing things because we were far away from the astrophysical prediction, and now we are more or less falling on the top of the astrophysical prediction. I mean, you find somewhere a statement that say, oh, the astrophysical prediction were wrong, we've been much more lucky than that. That's not true. I mean, you can really pull up the paper of 15 years ago and see that we are falling more or less into the top of the prediction. Yes, and if you want to translate this rate per volume in the universe, you have to use the galaxy density, which is 0.01 per megaparsec cube. So this translates to roughly 1 event per mega year per galaxy, per Milky Way equivalent galaxy, and this is a bit less for a binary neutron star and a bit less than that for binary black hole. So binary neutron stars are more often happening than binary black hole, but of course we can see to a shorter distance because they are less massive. So we have seen roughly 90 of these and only 1 or 2 of these. That's normal. Because binary black hole we can see to gigaparsec and binary neutron star we can only see to 100 megaparsec. Okay, and this is the summary of the detection. As you can see, as Virgo entered the game, the rate of detection went up because it could lower the significance of false alarms. And so we expect this slope correspond to, this is, you see the number of detection with respect to days, to time. So the slope of this curve is the rate of the detection. And this constant rate that we had in the third detection run correspond to roughly 1 detection per week, a bit 1 detection per 10 days. So this is where we ended the 03, the third observation run. We are, you see now, at the end of 2022, so we are in commissioning. And so March, April 2023 is the start of 04, that should last 1 year-ish. And then again, 2 year-ish of pause, and then 05. And 05 should be the end of these detectors. So this is 2028. Yeah, I know you cannot read, but I mean, we are here, end of 2022. Will be the end of these detectors in the sense that after 05, the detector should be upgraded to, the detectors are now second generation, and after 05 they should be upgraded to a kind of second generation and a half. Before we, in the 30s, in 2030s, then we should go to third generation. And third generation detector that will go underground. With underground, you can push the frequency down to few hertz. Then you can see something that is science fiction now. You can see binary, and you see this is advanced LIGO. You can see with this Cosmic Explorer and AT, which are third generation, you can see detection up to redshift 100, redshift of few tens up to 100. So basically, you can see all of the units. You don't expect to have black holes at, or neutron star at redshift 100 simply because matter didn't have time to collapse and form stars, and stars didn't have time to collapse. So in principle, we could see all of the binaries in the universe. And this is with LISA, even more futuristic, but not also for the next decade. We could see black holes in a higher mass range because LISA is in the space, so it doesn't have any problem with the lower frequency. We go to 10 to the minus 4 Hz, and so you could see up to redshift of 20-ish, and mass is up to 10 to the 6-ish, 10 to the 6, 10 to the 7. It really is scratching the limit of supermassive black holes. Whereas with third generation detectors, which are on Earth but actually under the surface of Earth, to kill the noise at low frequency, we get to few hundred, a few thousand solar masses. So we get into the range of intermediate range black hole masses, 10 to the 2-ish, 10 to the 3-ish. Whereas with LISA, we really get to 10 to the 4, 10 to the 5, 10 to the 6 solar masses.
Sorry, Riccardo, I didn't know about these underground,
Yes.
where are they?
So, Cosmic Explorer is the project to have it in somewhere in the States, probably in Arizona, because the project is to have 40-kilometer arms, so you must be kind of desert. The original project was to have a triangle. So in a triangle we have 3 interferometers, according to how you pair, and to have it underground. But of course, Europe, and it's a European project. Europe is densely populated, and so it's not clear where to build it. So now it's surging the idea to have, instead of one triangular, the 2 candidate sites were one in Holland and the other in Italy, in Sardinia. Now, since instead of making 2 sites and 2 national agencies compete, they are thinking, well, why don't we get money from both? And so probably the final decision will be to have 2 L-shaped, one in one country, probably Holland, probably Germany, and the second in Italy. And to have these 2 L-shape of third generation. Third generation means underground to kill the noise at low frequency, cryogenic, again to kill the noise. So, but it's still under debate, I mean, it's not decided. And the Cosmic Explorer is even, I mean, the Einstein telescope has been approved, not fully funded, but approved, in which design is not clear yet. Cosmic Explorer is a bit behind, in the sense that it's an idea for the moment. It's not approved, it's just a scientific community discussing. But we know, sociologically, the United States community, I mean, if they go for it, they can be, they can do it very quickly. Europe is always messy, and a lot of people to agree upon. So even though they have a head start, it's not clear that Einstein telescope will be done before the cosmic explosion.
How do you know there aren't any black holes in the beginning? You said it has to
Yes, well, because the black holes we see, they come from astrophysical collapse. So you need time, you have to collapse the matter to form the star has to finish the fuel, and they have to collapse. There could be primordial black holes that come from the collapse, the prompt collapse of primordial perturbations. But those are heavily constrained because if they've been there all the time, they could have been rise to lensing at high redshift and so on. Those are, I mean, it's not impossible, but they have never been seen and they are not required. Whereas the solar mass black holes, we see them, so they are required by observation and they are consistent with the present knowledge of the evolution. These primordial black holes, they could be there, they are constrained by the non-observation, but they could be there. And of course, yes, I mean, it would be a major discovery. If we see black holes here at redshift 20, 30, 100, there would be the fingerprint of primordial black holes born by prompt collapse of primordial perturbation. That would be, amazing. But it's not guaranteed at all. And also there are the primordial stars. The primordial stars, they should be around at the redshift 10-ish or 20-ish. But they are made mostly of light elements because they are primordial, and so they should burn very quickly. And it's not clear at all what is the end of their life. They might give rise to this early black hole, but we have not seen them. Again, if we see basically the fingerprint of primordial black holes or from black holes from primordial stars would be the redshift distribution. So the third generation detector will tell us. Once we see the redshift distribution, we know basically. And basically, this is the redshift distribution of the astrophysical black holes we know. So this is the redshift distribution of the black hole we've seen so far with LIGO. So this is a redshift, and this is the redshift distribution of the astrophysical black hole which are expected. The blue one is the theoretical prediction, and the green one is the theoretical prediction of the ones that will be detected by the Einstein telescope. That means that the Einstein telescope will basically see 90% of them, basically all of them. You can reconstruct the redshift distribution with the Einstein telescope, and then distinguish if they are primordial or not. And this is another way to plot this graph, basically. This is where most of the neutron stars are expected to be in the range of Cosmic Explorer, and where most of the black holes are expected to be in the range of Cosmic Explorer and Einstein telescope. There are this binary system made of compact object born by the collapse of standard astrophysical object. They are all recent. They are below redshift 10. If we see something beyond redshift 10, there will be some non-standard. Okay, so new line of research that are opened by this kind of thing.
Is it possible to observe like primordial gravitational waves, like beyond this redshift that you show, 100?
Well, it depends. I mean, they shouldn't be so much to make a stochastic diagram. No? So in principle, if they are there, these primordial black holes, they can give rise to astrophysical signals that they come from a definite direction, and we should be able to see it. But to make a real astrophysical diagram, there should be a lot, and there shouldn't be so many. They could make an astrophysical diagram if they're very massive and their frequency is very small. If the frequency is very small, then it's easier to make a stochastic diagram. So it's easier to make a stochastic diagram 10 to the minus 8 Hertz than at 10 to the 2 Hertz, no? Just because it's easier to pile up signals. And indeed, that's what maybe with a huge question mark pulsar timing array is seen. So, okay, it's not part of this talk, but there is a monitoring of the signal from pulsars from different collaboration, and the pulsars are very precise and very regular signals. And if they have some asynchrony, it could be due to the passage of gravitational waves. So there are two collaborations monitoring around 100 pulsars in our galaxy. So, and they've seen some effect that they could possibly ascribe to the passage of gravitational wave with a frequency of around 10 to the minus 8 Hertz. But it's not confirmed. For the moment, they cannot confirm it has the right pattern to be consistent with gravitational wave. they need more time, more data to collect. But the idea is that since you're monitoring pulsars over the time scale of years, the typical frequency you're sensitive to is the inverse of the year, which is 10 to the minus 8 Hz. So this is a completely different range, completely different observation, completely different data analysis. Seeing the pile-up of signal at 10 to the minus 8 Hz due to this gravitational wave coming, nobody knows from, but affecting the signal of pulsar which are really nearby, the pulsars in our galaxy, in our neighborhood. This is possible, but no way confirmed. Okay, and so what we can do with all this new physics? Well, we can do all of this, and now I'm focusing in the last 20 minutes on precision gravity. Any more questions on the observational side? Okay. So, basically what happens is that particle physics has been very, very, very useful to model and to make model of the sources that emit gravitational waves. And on the other hand, it's been very useful to give to particle physics, which have been bored of not having new data from accelerator, to recycle their tools. Why? This is the output of the real output that anybody can go on the website and download of the first event. You see it's a lot of noise and the signal is really a tiny little bit hidden in there. That's because it's swamped by the noise contribution. You see, the signal is something here, but you know, in time domain you get contribution from all these noise lines. So the signal is completely swamped with noise. So what you have to do is you correlate with your pre-computed template, and then you divide by the noise. What do you mean divide by the noise? The contribution to this time domain that comes from this peak, for instance, you want to kill it completely. So you go to Fourier space and you kill completely the contribution here at 60 Hz from the power line. You kill completely the contribution here from this noise due to the fact that the mirror is hanging and there's some resonant frequency. So you kill the contribution of all this noise, so you weight the correlation more where you have no noise, and what you get in the correlation, if you get the right alignment between the signal and the data, you get this nice correlation. Of course, if you compute the signal a bit wrong, you get also a very nice correlation, a bit worse, but also nice. So you have to be very careful in how faithful is your signal, because that would imply that you are basically misinterpreting the parameters of the waveform you want to get. And so, in order, what is important from the theoretical point of view to formulate to compute the waveform is to know the dynamics. Of course, the dynamics, if you know exactly the dynamics, I mean, I won't tell you how, but you can imagine that if you know exactly the dynamics, you can compute the waveform exactly. How do you know the dynamics? Well, you compute the energy function and the flux function. If there was no flux, no luminosity, the waveform would be very boring, would be a sinusoid, a perfect sinusoid, because the orbit would be a circle with no change in radius. Of course, there is the emission, so the circle is shrinking. So if you know exactly the function, the energy function and the flux function, you can compute the phasing and how it evolves in time. Basically, it is given by the ratio of the derivative of the energy function with respect to the velocity with respect to the flux. Here I parameterize the energy function in a post-Newtonian fashion. Post-Newtonian means in power of v squared, and the flux also in power of v squared, but you don't need to. You may have other approximation to compute these two functions, the energy and the flux. But the important thing is that you find a way to compute the energy and the flux. For instance, in the post-Newtonian, it's well posed the problem to expand the energy function and the flux function in power of v squared. So you see this is the Newtonian engine of the binary system, which is minus the kinetic energy, because kinetic energy plus potential is minus the kinetic for the binary system. And then this is Newtonian, then you have all sorts of correction, and you have this function which is the quadrupole formula, and then you have all sorts of corrections. And the nice thing is that well, it's a bit expressive, but the phasing, you see, is the integral of dv over v to the 6. So v is a small number, it's a velocity, it's smaller than 1. And it appears at the denominator to the power of 6. The large power here is due to the fact that the flux appears in the denominator and the flux is v to the 10. And so what happens here? This integral will have a large error. In particular, you want the phase of the waveform that you want to use for the match filtering to have a small error. So you want this series to be at least v6 correct, to kill the 1 over v6 and to give an error smaller than 1. Otherwise, you are trying to correlate the data with the signal which has a more 1 radians error. And if it has more than 1 radians error, it means that you are not predicting anything. So that's why you need to go to high precision. So this is good because it means that the match filtering, this is called match filtering, this correlation. you are doing is sensitive to high precision features of gravity, and this is bad because it means that unless you go to this high precision, you cannot really do mesh filtering. Okay, so for instance, and then you can target specific effects. So all of these are standard general relativity effects that give you this coefficient. In the post-Newtonian expansion, there is absorption in general relativity due to the fact that the gravitational wave is not only emitted, but the source itself can absorb, because the black hole doesn't let the gravitational wave go away. So this is a V to the 8 effect. And there is a tidal effect due to the fact that the sources are not point-like, they have some size. And if these sources can be excited and change their size, oscillate, then it would appear at first at V to the 10. So there are a lot of specific checks of general relativity that you can do, targeting specific effects. And once you have produced the waveform, you can, for instance, just let me show you the idea. The idea is this one. Is that you produce a wave, for instance, with total with a given mass fixed, but then you vary the mass ratio between the two objects, and you see the qualitative features of the waveform stay the same, but then the quantitative features of the waveform changes, and basically by fitting the quantitative features of the waveform to the data, then you are fitting these astrophysical parameters of your source. So this is what is done. Well, it depends a lot. On the spiral can be informally infinite if you start. Basically, well, if your source starts at arbitrarily large separation, the spiral can take an arbitrarily large amount of time. Okay. So for the typical sources we are seeing is that when we see in the last stages of the spiral, we see for a fraction of a second. For instance, the first event was seen over less than a tenth of a second. Whereas the binary neutron star, since they are smaller than the heavy black hole, we are seen over a minute. But usually with the on-surface detector, we cannot go beyond a minute. Because if you can, no, this is the noise. Cycles. Yeah, the cycles of order of thousands. 100 to 1,000, hundreds, few hundreds. Basically, the starting frequency of the signal is set by your detector. The ending frequency is set by the mass. So the smaller the mass, the higher the ending frequency. So for neutron star, you have the best situation in which you see hundreds of cycles. For binary black hole, the higher in mass you go, the lower in frequency you go with the ending. And for instance, the first event, there was a total mass of 60. You only see a couple of oscillations, 5, 6 oscillations before the signal ended. And so you see only a tenth of, less than a tenth of a second.
Do the detector ever be able to see something which is not approximately periodic? Just two things colliding? Or is it?
No, I mean, in the binary neutron star, we really saw the sweep of the frequency, so it's definitely not periodic. You see?
It's approximately. You're using a periodic approximation, right?
Well, that's to compute, but then when you compute the, this waveform is not, I mean, what do you mean
I
periodic?
understand, but you go to the previous slide, you say assume that.
Oh, yes. Then, of course, you have to stitch those analytic approximations with some numerical input, because, of course, when you get to here, the two objects are very close together. V is close to 1. G, all the nonlinearities of gravity are important. So, no perturbative method will allow you to make this transition. So, you match them. But then it's very important to have some analytic, because this part is very long and sets the initial condition for how to stitch the merger part, which is non-perturbative in any parameter you can think of. Unless you treat the system of the two objects as one very massive and one very light, and you treat it as a perturbation of a Schwarzschild. And then the same perturbative parameter, the mass ratio, will allow to go from here to there. The problem is that this approximation is very hard, and people didn't go beyond the first perturbative order on the top of Schwarzschild. Okay, so we compute the dynamics. Where do we start? Well, one post-Minkowski potential. We start with order G potential. Okay. So, I mean, this is standard, textbook computation. Anybody probably in this room can do it. Even the younger students. Just exchange one graviton between two particles, put an energy momentum tensor here, an energy momentum tensor there, and you get the one PM, one G to the 1 potential. The problem is that in this kind of way things get very complicated very easily. So basically at the moment people have solved only the G cube and almost solved the G4. The group in California and the group in Germany that almost solved the G4. And the problem is that as you go higher in order in G, the computation becomes very difficult. And then there is an orthogonal approach by Damour et al. That they basically try not to use a single approximation method, but use the result of all approximation method in a consistent way to predict the dynamics. So basically what happens is that immediately when you go to G square, this is one loop, you get already to some difficulties, and basically G4 is the state of the art. People cannot go beyond G4. One way to simplify this kind of diagrams, instead of using the full relativistic propagator, this full relativistic 4-dimensional propagator, one can split into 3 plus 1, and basically power the Taylor span k squared minus k naught, assume that k naught is small with respect to k squared, and then integrate over all of k. This is the post-Newtonian approximation, in which the graviton for which k naught is smaller than k is called potential mode. This is nothing but saying that the dynamics of the system is governed by the exchange of gravitational mode and do not change the energy. Of course, that's what happens in most of the cases in our galaxy. The Earth going around the Sun changes the direction, changes the momentum, but doesn't change the energy. Okay, so up to very good precision, what rules the motion, the binary motion, are those potential modes that change the momentum of the orbit, but do not change the energy. Okay, so this is what is called in the post-Newtonian approximation the near zone approximation, in which the energy exchange between the two particles is much smaller than the space, than the momentum exchange between the two particles, and then you can expand, and this ratio is smaller. Then you can do this, and for instance, the epsilon term in the propagator doesn't matter, and you can go on to many orders until this propagation breaks down. Until this approximation breaks down. It arrives at a certain point when you can also exchange gravitational modes that can go on shell, in which the k naught is of the same order of k. And this happened to the fourth post-Newtonian perturbative order. But basically, the post-Newtonian approximation is very powerful to make computation, makes computation more easily than in the post-Minkowskian, because basically what happens is that in this case, when k naught is of the same order of k, you can use another hierarchy of scale. In the near zone, you could use that the energy exchange was much smaller than the momentum exchange. Here, when the energy exchange is the same order of the momentum exchange, you can use another thing. You can use since the energy is of the order of the wavelength, is much larger than the size of the source. And so instead of considering the two sources 2 points, you can basically multiple expand. You can consider one source with structure and multiple expand. And that's also a source of high simplification of the computation. So now I guess I should wrap up in 5 minutes, right? Okay. So at the end of the day, what you have to do? You have to do some near zone computation in which you let the two particles exchange all sorts of potential modes, the modes that has energy much smaller than momentum, than space momentum, and add the exchange of these radiative modes, the modes that have energy also of the same order roughly of the momentum. But then you can use the other approximation of squeezing the two particles to one composite particle. Instead of 2 point particle, you squeeze the two particles to 0 distance and make them one composite particle. And there is a theorem that allows you to say that the sum of the two is actually reconstruct the full theory at a given, of course this is perturbative, at a given perturbative order, the full general relativity of 2 point particle is reconstructed by the sum of the near when they exchange potential mode and the far when they exchange radiative modes. And then you can say, well, instead of the potential I'm interested in the flux, then I use the far zone approximation and I compute the emission of radiative modes, and that by definition is related to the flux. I compute the leak of energy and compute the other piece of the information that I need. Okay, let me skip this. So let me just justify why we have to consider this kind of diagrams despite we're considering a classical situation. Of course, these are macroscopic objects, astrophysical objects going around each other, and they exchange momenta, which is which is big in Planck's units, and then we have to compute the typical potential. The typical potential is the Fourier transform of the amplitude of this process, of the scattering process. And basically, if you compute this diagram, you can see that you may think that this is quantum. Actually, in the QED course, well, in QED you don't have this because you don't have the track of interaction of the photon. But in QCD you can compute this, and this is certainly a quantum contribution because this is one loop. But what the basic observation is that the quantum contribution of this system enters order Q divided by M, where Q is the momentum exchange between the two lines, and just by dimensional reason it has to have an M as the denominator. But this means that in a power expansion in HQ divided by M is both a relativistic expansion and a quantum expansion. This is because if you send M to infinity, basically all this HQ over M to the 1, to the 2, to the 3 disappear, and you're left with the classical contribution. But this diagram has a classical contribution in the mass going to infinity limit, which is the astrophysical limit. This process is non-zero in the mass going to infinity limit, so the mass much larger than the momentum exchange between the two particles. This is classical, this is non-zero, and this is what you want to pick, basically. And so from the scattering amplitude, you get the classical limit by sending the mass to infinity with respect to the exchange momentum. And you will see that this diagram is not zero. It has a classical piece, it has a quantum piece that you throw away going to the infinite mass limit, but it has a classical piece. And that's why we have to do loops up to, for the moment we are able to do loops up to, so in the post-Newtonian we managed to go to, in some sector of the theory, to 6 loops. In the post-Minkowskian they managed to reach the 3 loops. But they are classical loops. They are classical correction to the potential, which involve loops, but are completely classical in the sense that h bar is sent to 0, in this sense that I told you. Because, you see, this is the Fourier transform. Q is not a momentum because the way I normalize it is just the inverse of the distance, because this is the conjugate variable to the distance in the Fourier transform. So here, if you want to make a momentum, it has to be multiplied by h bar. And so you write the amplitude, you expand in HQ divided by M, and you pick only the first term. That's the classical limit. If you do
this expansion is over the exchange momenta or the momenta in the loop?
No, over the exchange momenta. The momenta over the two particles here I consider in the non-relativistic case is the momenta of each particle. I take it basically as small on the top of the mass. Basically, these are small velocities, and so this is basically parameterized by the mass.
And the momenta in the loop will be regularized?
No, the momenta in the loop you have to integrate from 0 to infinity.
Okay.
So and
that is finite or?
Well, you hit divergences, but then you regularize the divergences in the usual way. So there are sometimes for the ultraviolet divergence you must introduce counterterms, but this only happens from 3p from the third perturbative order on, and so on. Sometimes, basically, because you have a near theory and a far theory, what happens is that the infrared divergences of the near theory are matched by ultraviolet divergences of the far theory, and they cancel. But this is just an artifact of our breakage, of our approximation. The infrared divergences of the far theory, they better not exist, otherwise her theory is inconsistent, and they do not, indeed. But yes, you encounter the usual problems of the standard quantum field theory computation. A nice thing that you encounter is that the far theory will have some ultraviolet divergences that you know how to complete with the near one. Basically, you know what you have a near theory where these objects are basically exchanging potential modes, and then you have a far theory in which these two objects collapse to a composite one. This theory might have a ultraviolet divergence, but that's completely natural because you know that this is not a point like. And what happens is that the divergences have a logarithm and a finite piece. The finite piece depends on the detail how you resolve the singularity. The logarithm is universal. And indeed, you can check in the full theory that the logarithm you obtain here are exactly the right ones. So
This cancellation is kind of a matching condition.
Exactly. No, it's not a match. Well, sorry, it's a matching. Absolutely.
It's matching.
It's a matching. The point is that the matching is really given by the physics. I mean, because in the standard model particle physics you are here, no? You have a hard theory, but you don't know how to resolve the singularity. Here, yes, we know how to resolve the singularity. We know exactly how the binary system is made of individual constituents. And so basically the matching is done on the basis of physics. So in the standard model you can only get the logarithm and you fix the finite piece by experiment. Here no, you get the logarithm and the finite piece and you fix by the matching to the full theory because you have both. This splitting is just due to simplify the computation. It's not there in nature, of course. And we have the theory for both. Okay, then you can use all sorts of methodology which has been developed in decades by particle physics, like tensor reduction of integrals. You can use the double copy, which basically you can map the square of gauge amplitudes into gravity amplitude with some caveats. You can have spin or unicity formula to reduce the length of your expression. You can use unitarity factorization to write loop amplitudes in terms of lower loop amplitudes. And by the end of the day, all these techniques are very useful. You can use it, but none of them really solved something that couldn't be solved by brute force. Now, the real stopping point, the real problem that everybody is facing in any scheme of approximation, either the post-Newtonian and the post-Minkowskian, is to do loop integrals at high loops. Basically, this is really the thing which is blocking people to go on. In the post-Newtonian, we managed to get to 5 loops in some subsector of the theory. In the post-Minkowskian, they only go to 3 loops, but going to higher loops in general is the thing to be addressed to go to higher precision. And you want to go to higher precision because there are new physical effects like the absorption, the tidal, the memory that only show up at higher perturbative level, and you really want to track them down. Okay, so for instance, this was the most difficult four-loop computation that we did. It actually happens that the 5-loop computation, the non-new master integral, all the 5-loop integrals, they can be mapped into 4-loop ones, just by the structure of the system. So this is the non-planar diagram, which was the hardest to tackle. And this is by today the hardest master integral that has ever been needed to solve the dynamics of two-binary system. And this actually, I say we solved, but it's a bit of misstatement because it was already being solved, but numerically, and then it was necessary to do what we just did. Basically, was a fit with analytic functions to get an analytic formula that reproduced the numerics, and basically that was the most difficult 4-loop integrals that was ever used. That was enough to solve all the 5-loop integrals. And so now that's one of the things that is stopping, preventing to go on. So the 5PN has been more or less solved. The 3PN has been all solved. The 4PM has been almost completely solved. There are some issues about memory stuff, but okay, I don't have time to enter into that. And this is just a summary of the standard approximation method that you can think of. The post-Newtonian theory works at large separation or small velocity. The perturbation theory works at a high mass ratio, so one or two object is much larger than the other. Numerical relativity only works when in the last orbits of the system, and so this is a region where you can use anything, where you hope to have some overlap, and then you can check mutual results, like we did to some extent. And then there should be a third axis in the or or we can recycle this RORM. Basically, it's the post-Minkowskian, where in the post-Minkowskian people keeps all the powers of the velocity and then keeps increasing power of g, like what is done in particle physics, and basically it also isolates this region of large distances when the power of g correction are less and less important. So basically the system is patched by different approximation methods with the goal to build the consistent dynamics for the binary system, with the goal to build waveforms that has to be matched to data. And okay, so I had something about cosmology, but I already used all of my time, so if people want to ask about cosmology, I will say in the questions. I stop here. Yes. Questions?
So numerical relativity is essentially solving Einstein's equations, or I mean, putting it on a computer, Einstein's equations?
Yeah, on a lattice, yes.
So why can't numerical relativity attack these questions?
Well, the problem is that you have very different scales in the problem. You have the scale of the gravitational wave, which is very long, no? Because it's related to the period of the system, and there is the scale of the binary distance, and then there is the scale of the black hole itself, which is even smaller. So in order to resolve all of these scales, you need basically a coarse graining of your system, both in time and space. And so basically to evolve some amount of time in the binary, you need huge amount of computer time. That's why you can only simulate the last stages of the orbit where the masses are comparable, because if the masses are not comparable, this is also introducing another time scale, no? Because if the mass is not comparable, the radiation is very small. So it takes a long time to coalesce. So basically the optimal system for numerical relativity is equal masses, comparable masses, so it radiates the most, and very close to the merger where it radiates the most. If you try to go away from either comparable masses or large distances, then the integration time becomes much longer than the actual time, basically, of the evolution. And basically, you wait 1 year and your solution actually evolved very little, so you don't gain
So
anything.
you see the perturbative method is progressing faster than numerical relativity?
So numerical relativity will be impossible to replace it for the merger part.
But I'm just asking you if you do comparing the methods, they're both progressive, right?
No, they're both progressive, but you can include new effect, new general relativistic effect. You can include the eccentricity. You can go.
No, I'm just asking which method is progressing faster.
Well, as I said, I mean they're progressing in different directions.
Okay.
So
So there's not much overlap. There's not much overlap. They're not competing.
no, they're really complementary.
Okay.
They're really complementary because so in numerical relativity, I mean, if you solve the dynamics, then for you it's trivial to include the eccentricity or circular orbit, right? It's just changing one parameter. Whereas for numerical relativity, it's highly non-trivial to move from one. So basically now they're trying to include newer and newer physical effects. Whereas in the post-Newtonian and in post-Minkowskian, you're trying, to push the perturbative order.
I have a question. Let me see if I understand the. So, just understanding. So, both numerical relativity and effective field theory generate templates which are used by LIGO and VILO in order to fit the experimental data. How does it work?
Yeah, not quite. Both compute the dynamics. Okay. Then from having the dynamics to compute the waveform is another step. This step is usually done within LIGO, basically. So within LIGO collaboration, people cook together all these ingredients from fundamental physics, from numerical relativity, or from analytic computation, and cook up recipes for waveforms, which of course has to be phenomenological because you have all this information, and then you have to make, a definite waveform shape. And the definite waveform shape will have some, some tuning, some fitting. It cannot be all determined from first principle. So you gather all you can from first principle, which is numerical relativity, perturbative computation, and so on. And then you have to cook up an effective model to have a specific waveform to feed into the data.
But anyway, they use your work and to generate templates that they need to compare with experimental data.
Yeah, I mean, basically, the two community, of course, are talking, but are a bit separate. So basically, people compute whatever they can compute on the analytical numerical side, they publish it, and then people in LIGO, they go and pull it and make a waveform or refine those. Usually people refine those which already have, because some waveform, of course, we have, and then people keep refining, introducing more effects, more checks, and so on.
Okay, just to make clear to students, what are the contributions that eventually they are going to give to science?
Yes, I mean, there is waveform construction and fundamental dynamics. There are two separate problems, which of course have a lot of connection. But people work on fundamental dynamics of the binary system, and then from all these ingredients to build a waveform is, I mean, is non-trivial, but of course it can be done.
Okay. Any other questions? Yeah.
So how many of these events would you need to measure each node as precise as its base and supernova?
Okay, I have a paper on that, but it's not in the slides. Basically, what happens? The supernova, yeah, it's not in the slide. The supernova, you're talking about cosmology, no? So in cosmology, we want to measure the luminosity distance versus redshift. So we know this relationship is very well linear for small redshift, but then close to redshift equal to 1 or something like this. Okay, so here there are lots of data supernovae up to 1 point something. So for gravitational waves, we have a lot of luminosity distance points, but each of these points have basically a huge error of redshift, so you cannot do much. But there is one point of gravitational wave data that came with a small error in redshift and with some error like this in luminosity distance. That is the binary neutron star at 40 megaparsec. So the idea is that if we can have roughly order of hundreds of gravitational wave data with redshift with small error, then we can get to the same we can get to the same precision as supernova. The problem is that to get a redshift with small error, we need the electromagnetic counterpart. And so the electromagnetic counterpart will be small redshift anyway, even if we can detect gravitational waves up to redshift 1 or 2, the electromagnetic counterpart will be a small redshift. And without electromagnetic counterpart, we have to rely on some other approximate methods to determine the redshift, like cross-correlating with galaxy catalogs. So we see something in some patch on the sky. We take all the galaxies in that patch on the sky. There will be one with the right redshift and 10,000 with the wrong redshift. That will give a much larger error, a much larger error on redshift. But if we can collect 100,000 of this gravitational wave detection, which have a large error in redshift, still we can get to a few percent in Hubble constant. So either 100 of detection with electromagnetic counterparts, but that will be confined a small redshift, or hundreds of thousands with no counterpart or with other statistical methods, and then they will be spread up to redshift 1 and 2. Each of them will have a large error, but if you have 100,000, you can reach the same thing. Or, of course, an hybrid thing. Use all the few you have with the electromagnetic counterpart and the 10,000 you have without the electromagnetic counterpart, and do the two. The problem is that to have 100,000 detection without electromagnetic counterpart, you have to wait for third generation, which means 10 years. If you want to have the electromagnetic counterpart, then with the second generation detector, we'll only have a bunch of them, 3, 4, 5-ish, we expect. Even with third generation detector, the electromagnetic counterpart will not be flooding, will be few tens. I mean, that's the prediction. So, I mean, we have to wait 10 years and see. I mean, this prediction has huge errors. We have to wait 10 years and see what are the figures. But for the moment, I would say, I mean, even with third generation detector, where we see hundreds of thousands of gravitational waves in a few years, order of 100 will be with electromagnetic counterpart. That's, I mean, of course, I can be wrong, but I mean, this is the expectation.
So if there are no other questions? Yeah. Maybe
Well, there are a lot of problems, no? Because if you change, the laser is shining.
Sorry, what was the question?
If you increase the sensitivity by changing the laser source. No, there is the mirror here. If you increase too much the laser source, then the mirror will start to heat up. If it heats up, then it starts to deform, and then you degrade the data. Then, you know, you have spent millions of euros to find a mirror, the exact solid state mirror that is exactly 99.99999% reflective to that laser. If you change the laser, then you have to spend again new amount of money to find another mirror that is 100% reflective to that other frequency. So, you know, there are a lot of fine-tuned constraints from technological point of view. But yes, I mean, if you increase the laser power, basically what you gain is a high frequency, because you can sample a smaller frequency on a higher frequency on a smaller time, because basically if you have a lot of power, then you are collecting a lot of photons even on a short amount of time. But then if you have a lot of power, then there's a problem of the heating of the mirror and the reflectivity of the mirror.
But it is easier to put the detector underground than...
So going underground is for the other end of the frequency. I mean, increasing the power will lower the, provided you can keep under control the mirror noise. It will also, because if you increase the power, there will be more momentum hitting the mirror, so the mirror might respond. You know. But if you increase the power, then you have more photons for a given sampling time, so you might hope to decrease this part of the noise budget. This part of the noise budget depends on the vibration of the soil, and those you get rid of going underground because the soil vibration are superficial waves. If you go, you should really go a few hundred meters down, which is not what they're doing because it's very expensive to go down. But still, if you go even 100 meters down, still you gain a little. You don't gain as much as you wish, but you gain a little bit. So, but to gain here, you have to go underground to avoid the superficial vibration or the seismic. Seismic doesn't mean earthquake. It means standard seismic. I mean, in Virgo, I look at the data of Virgo. At 5 Hz, you see, around 1 Hz, you see the wave of the sea hitting the seashore, which is 10 kilometers away from Virgo. And you see that signal in the data, because the sea, it's not the ocean, no, with the big waves, it's just the Mediterranean Sea hitting the seashore, and these waves propagating all the way to Virgo. Just to name one of the many sources of noise that you get as a small frequency.
Yeah, last question.
Yeah, you mentioned there's a triangular interferometer.
Yes.
And what is the advantage?
Yeah, it's the advantage with the price of 1.5 the tunnel. For an air shape, you have to dig 2 tunnels, and basically more than 50% of the budget of the new detector is digging the tunnel. If you make a triangular, basically with 1.5 the budget of that, you have 3 times as many interferometers. Okay, that's a big advantage. Of course, you lose a little bit because the signal is proportional to the cosinus. The signal difference is, these are the mirrors, is proportional to the sinus of this angle. So this is sinus of 90, this is sinus of 60. So you lose 2 over square root of 3. But then you gain the fact that you have 3 interferometers with 3 different pattern functions to look at the sky, at the price of having just 1 extra tunnel. But if you put the triangular interferometer, then you have only 1 country paying for it. If you put 2 L-shape, you have 2 countries paying for it. And I think what will make the difference in the end will be money. And if 2 countries can pay for 2 detectors, it's better than 1 country paying for 1.
Okay, so let's thank Riccardo once more. Remote is here to answer your other questions, okay? So just go to the job. Thank you, Riccardo.
Okay, thank you.